Thank you, everyone, for coming down today. First of all, my name's Andrew. I've been working in Google Cloud for about 4 years now. I think this is the third time we've run a GCP Next event in San Francisco. And every year we've run it, it's really been a step change increase in the number of partners, the number of attendees, the number of launches, and more importantly, the energy that we see at these conferences. It's really gratifying to see it grow so much every year. So truly, thank you for coming down today, and thank you for being a part of that energy and a part of this conference. Particularly, thank you for coming at this, which is probably the danger hour for a tech conference, right after lunch on a Friday. So hopefully we'll be able to keep you entertained. What we're talking about today is building high-performance microservices with Go, Kubernetes, and gRPC. And we actually realized when we were working through the structure of this talk, we kind of started with the title, and we realized that you could almost pick any single word in that sentence and quite comfortably make an hour-long talk out of it. And in fact, a number of my colleagues are doing so. Even right after this session, we've got Tim Hocken is going to be diving into the details of Kubernetes networking and the latest there. Dan Cerulli and Sepp are going to be talking about a thing called cloud endpoints, which I'll talk about a little bit too, but they'll be going deep on that. And then across the week, we've had a bunch of sessions on these topics that have usually picked individual slices of this and gone deep. So we were trying to think of what we could do to make this interesting, and we've realized that what we could do as a complement to some of these deep dive sessions was something that was a little broader and a bit more of an overview. So what we want to do today is show how you can use these technologies. Hopefully you've heard of some or all of them. But we want to show how you can use them in a real-world, practical, grounded application. So that's what we're going to do today. Today we're going to build and deploy an application to the cloud platform that uses all of these different services. And we're going to show you a little bit about that process and some techniques and some strategies you can use to turn that into a robust workflow. We're going to talk a little bit about some of these technologies as well and how they help us get there. So before we get into the app itself, it's worth just recapping a little bit of motivation. Hopefully microservices is a term that you've probably heard before. It's not a new concept for the most part. Fundamentally, it's about taking apart what might have previously been a large monolithic code base and breaking it out into discrete components that can be deployed independently. And particularly in the case, there's a number of advantages for doing this, but it's particularly advantageous when you are building an application that has a large number of developers on it. Being able to independently deploy and manage and implement each of these different components unlocks the development teams from each other so that they can work independently. It can be an enormous productivity boost. At Google, we're a very heavily microservice-driven company, or a service-driven company. When you interact with a site like Gmail, for example, when you go and view mail.google.com, you are triggering a cascade of RPCs across Google's data centers in order to retrieve the information and serve you that page. There's a whole ton of work going on behind the scenes, and as you do that, your RPC is passing down through the code paths that dozens and in many cases hundreds of engineers have worked on. So for us, being able to deploy these things independently is hugely powerful. So, and we've seen with cloud as well, there's been something of a resurgence in this as a design pattern. Again, for those who are around in the 90s, service-oriented architecture was another way of kind of saying the same thing. The general design pattern is not new, but a combination of elastic workload provisioning and some of these technologies have helped accelerate it and push it a little bit further back into the mainstream. So we're seeing it's becoming a very popular design pattern, a very useful one, especially in large organizations. But it comes with a couple of important challenges. Perhaps the most immediate and obvious challenge is, when you're taking apart a code base, where previously you were passing objects around in memory, now we're as often as not passing them across the wire. So to send a message, we have a bunch of work. To take a request to serialize it into a form that we can actually send as bits down the wire. That request then needs to get to a network card. That needs to get translated into packets. Those packets needs to get sent, and again, there's many hours of discussion you could have about that. All of this then needs to happen in reverse on the other end. The message needs to be deserialized and then turned into something that an application developer can use, some kind of in-memory object that they can actually work with. To do that, can impose a significant performance penalty. It's obviously a lot more expensive from a compute resource point of view to do all of this work every time you send a message. And particularly when you look at modern microservice architectures that may be composed of many tiers and many different operations like fan-out. As you push on this design pattern, this cost of serialization becomes more and more acute. Excuse me. So that's the first problem. In concert with that is another problem, which is just network contention. Part of this cost is just simply the amount of bytes and bits you have to send over the wire. When you're dealing with significant volumes of scale, when you're dealing with low latency or low poor reliability networks, network contention itself can be a problem. If you're not careful, not having a good model on your network architecture can impede your ability to take up a design pattern like this. And then finally, as you're breaking these things down into multiple components, usually you're breaking them down into multiple processes, multiple running programs. And when you take traditional models of application isolation, application containment, and apply that to microservices, often this incurs a certain degree of overhead that may be practical for something that requires a whole machine or several machines to run. But when you have a small service that just takes up a couple of megabytes of memory, maybe only needs a small amount of spindle usage, some of the traditional models of managing the compute resources that these services need aren't necessarily as robust or as elastic as we would like them to be. And just to emphasize that last point, it's worth mentioning bin packing. And so this is a somewhat simplified view of the problem, but in a traditional model of building applications, we may have separated our architecture out into a few services. But we will typically have at least one machine dedicated to each service, or maybe a cluster dedicated to each service. And again, that's fine when the services are quite large. It can often justify several machines to run those. But when you have a large number of small services, this model becomes problematic. It's much more convenient if we can run twofold. Firstly, run services across multiple machines, and secondly, run multiple services within a single machine. At Google, this is a real problem. This is something we started encountering a long time ago, as we had a large shared bulk set of compute resources. We've got a large number of developers deploying services into them. We wanted a way of being able to efficiently manage how services were being allocated to compute resource without necessarily having to get into the language of individual machines to individual services. So this fine-grained bin packing turns out, if you can do it, turns out to be a real advantage when deploying these kinds of systems. Again, not strictly necessary, not strictly required to couple this kind of deployment to microservices, but it definitely helps you if you can. So since we've been doing so much of this at Google, and we've been doing it for a while, we've spent a number of engineering cycles building out technologies that can help us in this process. We're going to talk about 3 of them today. In many cases, what you're looking at are the 2nd, 3rd, or 4th generation attempts at solving these kinds of problems. The first, and one of the most exciting, is a thing that we open sourced reasonably recently called gRPC, which stands for Google Remote Procedure Call. And gRPC is actually a collection of libraries and tools that allow you to create APIs, client and servers, in a number of different languages. And it relies on protobufs, which are a strongly typed and very binary efficient mechanism for serializing and deserializing messages. And it's also built as a transport on HTTP2. So it's able to take advantage of things like bidirectional streaming. And then on top of that is a robust library for things like flow control, rate management, retries, all of the work that ends up being necessary in building a robust, powerful client. But it usually takes a few attempts and a few mistakes in order to get right. The other thing about it is it's all open source. Second thing we're going to use is Go. Go is the language that absolutely has the cutest mascot. I'm sorry, smallest runtime footprint. And this, again, turns out to be important, especially when your services are small and you have a lot of them. It's not, again, strictly necessary to have a small runtime footprint, but when you can run your process as efficiently as possible with as little memory and as little system overhead as possible, this allows you to pack more and more of that capacity into a finite amount of compute, which saves you money. The other nice thing about Go, when it comes to microservices, it has a ton of interesting features in the language. But one of the things it has that's important when it comes to microservices is it has a modern and efficient networking library. Go is a relatively new language, which means, again, it's been able to learn some of the lessons of the past in terms of just how networking can be performed and abstracted. And it's been used very, very heavily at Google for networking applications. And so we've had a lot of time and a lot of energy spent into making these libraries as efficient and as optimal as possible. They're also nice and easy to work with, and again, Go is open source. So there's a community out there that you can, you don't just get it for free, but there's a community that you can engage with. And I don't want to make this too academic a discussion or too academic a talk, but it is worth talking a little bit about performance. The graph here is actually from a public benchmark that the gRPC team published. They rerun this benchmark with every release of gRPC. It's a thing called the ping pong test, where you have two VMs and you just take a message, serialize it in a client, send it to a server, deserialize it again, send it back, and repeat, I think it's about 100 times. And measuring the latency of that process. So it's a really good measure of the performance of the language and the runtime at dealing with this message passing. And you can see Go does really well here. It's approaching the kind of performance you get out of C++. And also, although it's not on this list, Java. So while gRPC is very much a language-neutral technology, it works really well with Go, which is why we like it. The last key piece in this is Kubernetes. Again, there's a lot of talks right now on Kubernetes, so hopefully you've heard something about it. Kubernetes is the spiritual successor, in many ways, to a technology that we've been working on at Google for a long time called Borg. Borg is our hosting platform that allows us to, again, solve the bin packing problem, taking a large number of tasks that a large number of Googlers are submitting to a system, and it effectively acts as a giant solver, figuring out where is the best place on my fleet to run that at any given time. And when these workloads are not just being deployed all the time, but they're also dynamic in terms of the resources that they need to have access to, being able to have a dynamic automatic system that's able to handle this allocation is hugely powerful. With Kubernetes, we've taken that exact same philosophy and many of the same ideas, and we've packaged that into an open source project. Interestingly, it is itself written in Go, although like gRPC, it works perfectly well with any language. It's very much a language agnostic piece of infrastructure. Also, open source and a very thriving community of people building around that as well. And I think more contributions of Kubernetes, more commits, have now come from outside Google rather than inside. So we want to build an app and show how all of these things can fit together. If we can cut to my laptop quickly, which I may need to wake up. So we're going to build an app. The app does this. It creates 3D animated GIFs. Super practical. I hope you can see how this applies to your day-to-day lives already. So super practical. One of these apps that is actually a little deceptive. Very simple to use, very simple to show, but there's a lot going on in order to make this happen. I'll try this live and do my ritual prayer for the demo gods. But let's see what this actually looks like to use this app. So we have a very simple form. I'm going to put in a name. I'm going to choose a mascot. You've seen the Go one, again, cutest, right? I'll pick something else, say gRPC. We'll go create an app. Now, so we've now submitted a job. We're using a technique called path tracing to actually generate that 3D GIF, which is a particularly computationally intensive exercise. And so in order to make all of this happen, we've actually had to do a ton of work. The first thing we had to do is create a series of scene assets to render that image. Things like materials files, object files, a bunch of metadata about light sources and camera placement. And we actually generate that dynamically for every single GIF that needs to be requested. So we've gone and created a bunch of those assets. The next thing we've done is create a task to render each and every frame of that GIF. There's about 10 of them. And so we've then submitted that, and we're done. It's actually faster than it took when I practiced this. We had to submit a task for every frame of this animation, and then we've then gone and dispatched that out to our cluster. Our cluster has then gone and run that rendering process. It takes about, it's a pretty slow library that we used, so it takes about 15 to 20 seconds to render each frame. So it's doing that in the background, pulls them all together and synthesizes them into an animated GIF. So quite a bit of work there just to handle all of that, overhead. And if we switch back to the slides, we can dive into the architecture of this thing and take a look about how we actually built this using these technologies. So what we're seeing here is basically the set of services that we needed in order to build this out. Would you believe 5 services are needed to build 3D animated GIFs? So let's break this down a little bit. Let's start with the first service, the bottommost service, which is the renderer. So the renderer is actually a very general purpose service, which is nice if we ever want to reuse animated GIF creation for any other purpose. What the render service does is take a request that includes references to all of those assets that we talked about. So again, objects, materials, light sources, and so forth. Will perform the task of actually generating an image. It will store that image in Google Cloud Storage, and then it will return in the response back to any upstream caller a path to where that single frame, that single image lives in Google Cloud Storage. On the other side of this, we have the front-end service. The front-end service is the service that we were actually interacting with directly in the browser there. This is the essentially HTTP server. So it's handling the form, it's handling the form submission. If we were doing user authentication, it would probably do that. And it does all the kinds of things you would normally expect to see in a web front end. It serves static assets and things like that. There's not a lot of logic in the front end, though. We really wanted to keep the logic out of the front end as much as possible, because we never know if we might need to be building front ends for other things. Maybe there's a mobile kiosk we want to build, or a mobile app that we want to build that doesn't necessarily need to talk to a HTTP API. So we really wanted to try and encapsulate as much of the business logic, if you will, of the GIF creator into some other service. So we called this, of course, the GIF creator service. GIF creator does everything in between our web front end and our renderer. GIF creator takes has an API of its own. It takes an API request that looks a lot like that form that you saw before. So there's a caption. You can pick a mascot. There's a couple of other little bits of metadata. And it will, when it receives that, it will then do all of the work that we talked about. It'll be creating the scene assets. It'll be storing them in Google Cloud Storage. It will also be responsible for calling out to the render service. So it will call the render's own API and perform the fan out in order to make that happen. We want to do that robustly, so we've actually split this into a server and a worker, and we use Redis as our state management service to track the status of all of these jobs. GIF creator handles all of that. It actually has its RPC and its response. It doesn't send back the GIF because we expect this process to take a while. Instead, we send back a job status, which the upstream front end can poll for as necessary in order to see where this work is at. So GIF creator is really the kind of the workhorse of all of this. Of course, GIF creator also does that synthesis, the compositing of a set of frames once they've all been rendered into a final image. So a lot of work going on here. Let's zoom in on the APIs for a second. There's really 2 APIs that we have for the 2 different services, the render API and the GIF creator API. We've talked a little bit about what those APIs do, but let's jump into a little bit of code. We wanted to write these APIs in gRPC. Again, we like the fast serialization, the efficiency on the wire. We like all of the retry and flow control that gRPC gives you. gRPC APIs typically start with a document that looks a bit like the one you've got on screen here. This is called a proto file. A proto file is actually a language-agnostic, domain-specific language for describing an API. And it's describing 2 things, both the RPCs, which endpoints you can call. Most crucially, though, it's also describing the messages that get passed in the request and the response. The takeaway really from this screen is that this document is it's quite strongly typed. You can see we've got things like enums here. We can describe quite complex data structures. Although we haven't had them here, we can have things like repeating fields and arrays. And so it's a robust language for describing message passing. And as I said, this is language agnostic, although it looks a bit like Go code, it isn't. But what this then can be used for is 2 things. One, is it's a fairly human-readable contract for describing what this API should be. That in itself is actually pretty useful. Two different teams who need to talk via an API can use this document to effectively negotiate on what it is that what RPCs they need from each other and what information they need from each other. Especially when they work in different languages, having a language-neutral document like this can actually be a really nice idea. The second thing that we get out of this document, though, is an input for a tool called ProtoC. So ProtoC is the protocol buffer compiler. And what ProtoC does is take this document, or a document like it, and can turn it into client and server libraries in your language of choice. I think from memory we support about 7 different languages at this point, and certainly Go is one of them. And I won't demo it to you here, but when I run ProtoC over a file like this, I then get a library generated, which I can then use in my code. So this is some actual code from the GIF creator service. It's a little, I've cut a bit out. But this gives you an idea about how this generated code from a proto file can be used in my service. And if you've worked with really any kind of client-server interface, this will look fairly familiar. There's a lot of options and things that you can play around with that you don't necessarily need to deal with by default, but you can certainly get into. Things like injecting middleware, things like supporting different forms of authentication. But fundamentally, it's a very simple, particularly in Go, construct to work with. Crucially in this, you can see that the objects that I'm dealing with in my Go code are Go objects. I have Go structs. I have Go arrays. I have Go strings. So I'm working in a form that's pretty idiomatic and pretty natural. I haven't had to deal with any of the serialization and deserialization. gRPC's handled that for me. So now we'll get back into the code in a second, but one of the things that we found really trips people up, it tripped me up a lot when I was first starting to work with these tools, is actually building the pipeline that gets us from code like you saw before to something that's actually running up inside Kubernetes. It's complex because frankly there's quite a few different steps involved, and there's many different ways of accomplishing those steps. There's not necessarily one single blessed path that everybody uses. So we wanted to talk about that a little bit, not to show the canonical way necessarily, but a way where we can get from a code base to something that actually runs. And as I said, there's a lot of steps. The 2 key steps, the 2 high-level steps, if you will, are the build and packaging phase. This is about taking code and turning it into an image, a binary asset. Typically, that's a Docker image, but you can pick your packaging format of choice. And you'll usually store that in an asset registry somewhere. Maybe it's Artifactory or Docker Hub, or you can use, we're going to show Google Cloud Repositories, Google Container Registry, which comes with every Google Cloud project. Second stage is about deployment. I've built this asset that describes everything I need to run. I then need to get it into Kubernetes and deploy it. So let's double click on that first stage. This is what the build pipeline looks like for going from source to an image for this app that we just showed you. And there's actually quite a few different steps in there. This is especially true when you think about compiled languages like Go or C or Java. It's a lot more than just getting some code up and running on a server. We really actually rely on these pipelines in order to be able to do it. The first step is getting the dependencies involved. Pretty straightforward. Go, for those of you who are Go developers, you'll know there's plenty of dependency management tools. In this case, we used Glide, although I encourage folks to check out dep, which is gaining a lot of traction. But you use a package management tool of some kind to bring in all of the necessary dependencies that you have in your application, anything you haven't checked in. Particularly important if this is on, say, a CI server or it's a clean room build of some kind. The next step is you need to actually build your binaries. You need to run go build. Now, in our case, we have 3 services that we're actually building ourselves. So we have 3 binaries, 1 for each of them. In our case, all of these binaries come from the same code base, and we're actually going to package them into the same image. We're just going to invoke that image differently for each service. Now, you don't have to do it this way. Again, you could have separate binaries, separate images, even separate languages for every different service here, but for convenience, we've packaged it into one. And we're Google. We like the monorepo thing, I guess. But you have 3 binaries, and then we have these binaries, we need to package them into an image. So in that image, this image is this hermetically sealed unit that contains everything we need in order to be able to run our app. So obviously we need the binaries in there. We don't need the source code. We don't need the build tools. But we do need a few other assets. The web server, for example, needs images, CSS files, templates, a bit of extra stuff in order for it to work. The GIF creator service needs canonical copies of all of its asset files. So there are a few resources in there that are necessary in addition to the binaries in order for this thing to run. And then once we packaged it, we need to get this thing into a registry somehow. Now, when most people start off with this, usually what they end up doing is building, usually some kind of, I don't know, shell script file or some other tool to help coordinate all of these steps and bring them in together. And that works pretty well, although you do run into some challenges with that model. One of them being you actually need copies of all of these tools running wherever you're running that script in order to run the build process. So we found at Google, a lot of teams have this problem as well. A lot of our customers have this problem. So we've come up with a tool that helps. It's called Container Builder. We shipped it a couple of days ago, actually. Container Builder does exactly what it says on the tin. It takes source code and packages it into a Docker image. And it supports a language for describing these kinds of pipelines that we've talked about. It's called, it's a YAML syntax. The file is usually called cloudbuild.yaml. And again, I won't dive into the details here, except to say that we have a cloud build YAML file for this project. We've checked it into the same repository that we have all of our other code. And this describes the 3 steps that are necessary in order to build our app. Everything is included in this file. The way we describe steps in Container Builder is actually with Docker images themselves. So the nice thing about this file is it can actually be taken and run by anyone else on my team, even if they haven't necessarily installed all of the tools like Glide and Go and Docker before. So it's a pretty neat way of describing a build process, and it's pretty general purpose. Again, we chose things like Glide and Go Build and Docker Build to package everything, but you can pick up other tools if you wanted to. Practically, how do you actually trigger a build like this? You've got 2 ways. One is, of course, there's a gcloud command to do it, and that can be done from any source tree that's sitting on your laptop. But we also have, and again, this was just launched a couple of days ago, an extension to container registry called Build Triggers, which allows you to watch any GitHub, any Bitbucket, any Google source repository that you might have set up, and every time you do a commit to a particular branch or a particular tag or that follows a particular pattern, you can automatically trigger a new build in container registry. So I'll give you a quick demo of that now. Hopefully you can see this. I'm looking at Google source repositories here. This is the source code of all 3 of those services. Just jump into front end just to give you a sense of it. This is the front end. This is the Go code that produces the binary for the front end. Some static assets in there. And some templates and a few other little things. If we jump back out and look at the root folder here, we're looking at the master branch. We've also got some pretty familiar looking files that help us with the build process. So here's our Glide file that describes all of our dependencies. Here's the cloud build file that we showed you a couple of seconds ago. And we've actually also got a Docker file here too. I mentioned there was a packaging step. We're using Docker to perform that packaging, and so it'll pull from this Docker file. And you can see there, if you're not familiar with Docker files, this probably won't mean much to you. But if you are, the interesting takeaway from this Docker file is there's really not that much going on. All it's doing is copying in the binaries that we built upstream and adding the templates and a few other things. It's creating some root certificates. But otherwise, it's really not doing very much. It's a last mile packaging step. And this is really nice. It allows us to keep all of our build tools out of our final image and allows us to create something that really only has the bare minimum we need in order to run it. So down here in Cloud Shell, hopefully you can all see this. So this is a local VM I've checked out. You can see that same repository. So I'm going to try and make a quick change here. And for the sake of this demo, I'm going to make a boring change. I'm just going to jump into the front end. And what I'm going to do is I'm going to make that form that you saw in the form that you fill out to create a GIF. I'm just going to change the color of that just to prove that just to prove this deployment flow to us. So if we look at that, it's form.html. Okay, we have a header here. So I'm going to do something really trivial. I'm just going to add something like that. So I made the change, simple. Let's commit that back to our repo. Okay, so we've pushed that. So now, if we jump over to container registry, let me give you some room. If we jump over to container registry, you see here we have this list of build triggers. So we've set up a trigger already to watch that repository, and every time we push to the master branch, it's going to automatically trigger a build for us. If we jump into build history here, we can see that build is actually kicking off. And I won't bore you with too much of the detail here, except to say here's the logs of the process. So right now it's going through the glide, it's running glide to bring in all of the dependencies, and then it'll continue on with the build and the remaining steps. Something interesting to note here is that every build is given a build ID. This is just a UUID. And in our cloud build file, we've, actually let me show you that really quick. In our cloud build file, we've actually configured it to generate our Docker image with a tag based on that build ID. So we've asked insert the build ID into the final image. So let's jump back. That might be done by now. And it is. So there's our build. And if we jump into container registry and look, and we have a new image. Great. And just a quick look at the size of that image. It's only 15 megabytes. And if you're used to dealing with Docker images built from Ubuntu that have a ton of tooling in them, 15 megabytes is nice and small. So now we have an image. Next, we want to get it into production. So now we want to talk about deployment. Before we do that, though, so you'll notice again this thing has a tag based on its build ID. For Kubernetes, this can be really useful because we're going to use these tags in our deployment manifests. Now we could use the UUID that I got created here, but that's a lot to remember and a lot to type. So I'm actually going to add a second tag here called demo fix, which we can use a little later when we're building out when we're doing a deployment. So if we can jump back to the slides, let's just talk about what this deployment actually looks like. So what does this thing actually look like inside Kubernetes? Kubernetes has a number of constructs that are really useful in this process. Again, it could be easily an hour talk just describing the different moving parts of Kubernetes that come into play when you're running a real service. We're really only going to talk about two of them. The first is deployments. So a deployment is a concatenated object in Kubernetes that actually in turn describes a number of other underlying constructs, a replica set and pods and pod configurations. And it just provides a really nice declarative way of describing how all of these things are constructed. Fundamentally what a deployment is doing is telling Kubernetes how to run this image, how to run this code. And if we actually have an example of what a deployment looks like. This is a simple, slightly simplified deployment spec. What this deployment is describing is take an image that we have sitting in a registry somewhere, run that image using this command. So this is the front-end service here. So we want to call that front-end binary that we built before. Describe any other metadata that this thing needs. So what ports does it need? What environment variables does it need? You can describe other constraints, like what's the minimum amount of CPU this thing needs? How much memory does it need? But fundamentally pretty simple. How many replicas do we need? How many copies of this process do we want running across our cluster? The other component is services. So it's going to get a little meta, but we're going to build services for services. So a Kubernetes service is a way of just providing a simple static endpoint that we can use when we used to help us in talking to all of these different components. With deployments, we might be describing a number of different processes running all over our cluster, we need a way of being able to discover where they are and being able to get traffic to them. So a service in Kubernetes helps us do that. The way you can use a service really depends on your deployment. It's a very flexible descriptor. In our case, though, we have the 3 services we're building all work basically the same way. We want to have a stable internal DNS name for each of them, so that if we need to refer to them from another service inside Kubernetes, we can just look it up by its DNS name. And then what we want is a load balancer which can dynamically route traffic to any of the pods, i.e. the running versions of this process, at any one time. So this manifest file describes everything we need in order to be able to do that. And we have one of these for each of our services. We also have one for the Redis service that we're running inside Kubernetes as well. So now we're going to run another quick demo. So if we could switch, great. So we've built this image. Let's get that image into Kubernetes. So in our source tree, we have this directory k8s. And in that k8s directory, we have a set of YAML files that describe these deployments, basically the same thing you just saw on screen. Now we have 3 services, and each of those has a deployment manifest and a service manifest. So in our case, what we want to do is update the front end. And really all we want to do is tell that front end service, instead of pointing to the old image, now we want you to redeploy, now we want you to be running the new image. So if I increase this a little bit and jump into that file, you can see here is the file. I like environment variables, so I've created a bunch of them for this project. And this here is the image that's being used to render the front end. You can incidentally run multiple different images inside a single, what we call pod in Kubernetes parlance. But in our case, we're just going to do one. And we're going to pull from a different tag than the one we did previously. And I think it was it, what was it again? Was it demo fix? Yeah, demo fix. Okay. So we've updated that file. Now we need to tell Kubernetes. To deploy it. So let's go do that. Okay. Deployment replaced. Now, it's worth unpacking that last section a little bit because a lot just happened. We didn't tell Kubernetes that we wanted to replace an image. What we did was tell Kubernetes that we would like the state of the system to change to match this new file. And one of the things that's different in that new file is the image has changed. It's kind of important that we described it that way. We didn't say make a change. We just said we have a new idea of what we want the state of our system to be. Kubernetes, go and figure out how to make that happen. Now, we can provide hints as to how Kubernetes can make that happen, like deployment policies. But at the end of the day, this is Kubernetes' responsibility to figure out how to make it work. And this is, again, a really powerful idea in Kubernetes, that you can declaratively describe the state of your system and have Kubernetes figure out all of the thorny details about how it should actually work. So let's actually, moment of truth here, see if this actually worked. So I'm going to jump into our Kubernetes dashboard. You can see, again, all of the deployments. This is our running cluster. This is running across 10 nodes, which might be a little excessive for a GIF creator. We have a front-end deployment here. And we can see a minute ago, this thing received a new replica set. So a replica set is the, so what Kubernetes did in the background was create a new replica set that describes the set of running pods that we need. This new replica set would have the new pod configuration in it, i.e. with the new image. And it will spin up that, it will gradually increase the size of that replica set while spinning down the old one. And so what you get is a graceful deployment as we shift from one mode of a system to another mode of the system. So that actually happened. In our case, it's a pretty simple system, and we're not really doing much in the way of health checking or any other thing that can potentially slow this down. So in our case, it just happened in a second or so. But we have now a new replica set. And you can see here, it has 2 pods in them. Pods aren't doing very much yet. But if we jump into one of them, we can see that this is now running with the new image. And it looks like it started perfectly well. So now, if we go back to our GIF creator, we go back to that entry form, our text is in red, so our change went through. So that is hands down the biggest applause I've ever got for changing a bit of CSS, so thank you for that. So now we have a running app running in a cluster. We've only got a little bit of time left, and I want some for Q&A. So I'm going to do a whirlwind tour of some of the things that you get when you run this stuff inside Google Cloud. Everything I've shown you up until now, for the most part, with the exception of Google Cloud Storage, perhaps, you can run basically anywhere. In fact, most of it you can run on your laptop if you want to. And again, all of this stuff is open source. That's pretty nice. It means you don't really need to pick Google in order to get started with this stuff. But if you do happen to be running it on the platform, you get a couple of interesting advantages. The first, of course, is you get Google Container Engine, which takes away a lot of the headaches of actually running a Kubernetes cluster. And it can do a lot of things for you, including automatically patching nodes, automatically standing up, say, Google Cloud Platform load balancers in order to make your service run. It can do dynamic auto-scaling, a bunch of other nice plug-in features there, and it takes a couple of clicks to use. But there's a couple of other features that turn out to be pretty powerful on the cloud platform that are worth touring through briefly. We saw Container Builder, we saw source repositories, we saw the container registry. We also have a built-in tracing system, which works really well with Kubernetes and gRPC. So this thing, I won't bore you with a full tour of this. But this allows us to do distributed tracing across a cluster. Distributed tracing is actually really useful in situations like this. You know, one of the first things that I wanted to do once I deployed this app was figure out why it took so long for us to render a bunch of frames. So by jumping into tracing, you're able to understand, even as a job progresses, where the time is being taken. Is it being taken up in rendering or passing to cloud storage, or is it in the Go binary? Distributed tracing allows you to instrument your code, and when it's distributed, a nice artifact of this is you can pass trace context across multiple running processes. gRPC in particular makes it really easy to do that. But by doing so, you can actually die trace a request all the way from when a user requested it on our front end, down through to the fanned out tasks that were being run in the renderer, and all the way back up to the final job. I won't demo that now, but would make for a good follow-up talk. Incidentally, what you're looking at right now is the breakdown of latency over time. You can see there's a few experimental tasks there, which took a really long time to run. And generally, you've got a clustering that looks a little bit like what you'd expect. Some of these dots represent our front-end service, which is really fast and responds to requests very quickly, terminates very quickly. Some of these represent spans of longer jobs, e.g. the entire process of rendering an image end-to-end, or just calling the render service, which takes a bit more time too. So we have tracing. Of course, logging is centralized. If we jump back to the slides, I'll cover a couple of other quick nice features of the cloud platform. The other one is the live debugger. So if you want to do real-time introspection of application state, the Stackdriver debugger now allows you to do that. It works really well with Go, and it works with Kubernetes. The other thing is Google Cloud Endpoints. If you haven't heard of Cloud Endpoints and you're interested in this, Dan Cerulli is giving a talk on this right afterwards. What Cloud Endpoints allows you to do is to provide some additional robustness and automation and centralization around your APIs. Happens to work really well with gRPC. And this gives you features like a dashboard for detailed logging of RPC traffic, for detailed monitoring of your RPCs and latencies, again, across a system if necessary, and things like centralized access control. So if you ever get to a point where you're thinking about publishing one of these APIs to make them consumable to the rest of the world, all of those things that you might need to think about, like user-based quoting and ACL management, Cloud Endpoints grossly simplifies the process of building out. And again, works really well with gRPC.